All right, I have shared the YouTube link, so let's get going. Okay, first let's discuss this superconductivity in the what we call as zero-dimensional limit. Zero-dimensional limit actually is just a nomenclature, slightly misleading, but it's used quite extensively, and it refers to actually small particles. So let us ask first a question that if I take a small particle, let's say, which is nanometer size, how small can a superconductor be? So for that, you have to start with the concept of Kubo gap. Now, what is interesting is that you know that superconductivity has two length scales which are fundamental. One is the coherence length and the other is the penetration depth. And very naively, you would have thought that when these two length scales, one of them would probably determine the limiting size of a superconductor, below which you don't have superconductivity. Now, surprisingly, the fact of the matter is that neither this nor this decides that limiting size. The limiting size is decided by a completely different length scale. And the way you can get that length scale is the following. You know that if you take, let's say, particle in a box, then you have these discrete energy levels. Okay? You know that if I, let's say, reduce the size of my box, then these energy levels would become, the spacing between energy levels becomes much larger. So in a solid, normally, you have the conduction band. This is the Fermi level. And this, this axis is, let's say, the density of states. And you have all these states that are filled. But these states, they are so the number of states in a band. What is the number of states in a band in the solid? Jaideep or Gurachat, what is the number of states? What is the number of energy levels within a band in a solid?
I mean, it is infinite, right?
How can it be infinite?
Or,
it is capital.
No, I mean,
it is what?
Number of primitive cells.
See, you are starting with atoms. Each atom had an orbital, at least one orbital. Maybe it has more, but at least one orbital. So these orbitals come together and they spread in energy and form the band. So therefore, in a band, you will have exactly the same number of energy levels as the number of atoms that are contributing to the band. Okay. So therefore, the number of energy levels is n. This n is a very large number for a large size sample. But if I take a very small size samples, then n is small. And when n is small, it means that here the bandwidth roughly remains the same. But now I have much smaller number of energy levels. And in an extremely small particle, I will have, let's say, few energy levels. Now, this is the extreme limit. But what is happening effectively is that as I am reducing the particle size, the energy band, which had a continuum of energy levels, now is having discrete energy levels. So, these gap that opens up, and that you can very easily calculate just based on particle in a box. This is what is known as the Kubo gap. So I have shared the article by Bose and Ayub, the review article in Reports and Progress in Physics. This is shared in the Facebook group. And the concept of the Kubo gap and the derivation of the Kubo gap, you will all find it in that review article. So now, when this Kubo gap becomes larger than the superconducting gap, then this was my Fermi level, and all these electrons here, let's say the electrons which were within, let's say, a value delta from the Fermi level, these are the ones which became Cooper pairs. These are the ones which become super electrons. But now, since this is the Kubo gap, I don't have any electrons here. So there is no electrons to contribute to the pairing. So therefore, the absolute limit of the size at which superconductivity is destroyed is when the Kubo gap becomes equivalent to the superconducting energy gap delta. Is that understood? Any question?
Sir, can you please repeat why they are not Cooper pairs?
Well, for Cooper pairs, you need to have electrons.
Yes. Yes.
This is the Fermi energy. The next
Yes.
energy level is here.
Yes.
And the delta is smaller than this. So where are the electrons here? There is no electrons here to pair.
Yes. Yes. Yes.
Alright? So the basic concept is very simple. Alright, so this is what is the limit of superconductivity, and typically this happens below 10 nanometer. So for example, in niobium, this happens at 8 nanometer. Let me show you some data. This is so let me show you that it really, this Kubo gap concept works. Give me a minute. All right. All right. So This is some work that we had done several years back, and this was one of the early proof that this criteria that I mentioned to you, this criteria is called Anderson criteria, and actually Phil Anderson developed this criteria in 1959. Now, this we verified at that time for niobium. So, for example, you start with niobium films. So, these are niobium films that are deposited with sputtering, but they are not films that are, let's say, smooth uniform films. These are small particles that come in contact with each other and form the film. So when you have a particle size of 60 nanometer, then the TC is the bulk niobium TC, which is 9 Kelvin. Then as you reduce the particle size, the Kubo gap starts appearing. And when the Kubo gap appears, then you will have less and less of number of electrons that are able to pair up. So therefore your TC drops. And then at 11 nanometer, your TC is about 6 Kelvin or so. Below this, at 8 nanometer, you don't have any superconductivity left. So here, if you see, this is the variation of TC. The TC variation here, there is practically no effect of the particle size. Then it gradually decreases, and at 8 nanometer, you destroy superconductivity. So you can actually, so there are many other things that you can do. You can measure the superconducting energy gap. By the way, this is another example where we had used Andreev reflection spectroscopy instead of tunneling spectroscopy to measure the superconducting energy gap of these small niobium particles. So one could in principle have used tunneling spectroscopy as well. So this is this, you see that as you reduce the particle size, the TC decreases, and in proportion, the gap also decreases. So the attractive pairing interaction keeps on decreasing proportionate to TC. That's quite easy to understand because your attractive pairing interaction is N0V. Now, in that particular energy interval, if you have smaller and smaller number of states, then effectively you have a depletion of the density of states. So N0V is decreasing and you gradually decrease TC. So these, in fact, later on people have checked the Anderson criteria in many superconductors. We have also, let me show you, maybe I can show you this Anderson criteria also in lead. So you see, these are how these films look like. So you have these small superconducting lead particles, and they are separated by an insulating layer of lead oxide. All particles, so when you make samples like this, all the particles that you have are not exactly of the same size. You have a size variation. Now, I will show you later on. So this is again the Anderson criteria that you see. I don't exactly remember what was the number in this case, but you have here the TC, which is fairly constant, and then it precipitously drops around I think 6 nanometer or 5 nanometer. I don't exactly remember the number. It's a long time back. Yeah, up to 7 nanometer, I can see that there is a TC. So must be about 6 nanometer or so. Okay, so this is one of the very important aspect of nano superconductivity is where is the cutoff for superconductivity. If you want, that's a starting point. Now, let these experiments later on have been done with scanning tunneling microscope, and in STM, when these experiments were done, you could access individual nanoparticles. So you did not, here we are doing a compacted film and we are measuring the entire film. There with a STM tip, you could measure individual particles and then look at the Anderson criteria and so on. There are some limitation of looking at individual particles. For example, on an individual 8 nanometer or 5 nanometer particle, you cannot measure the electrical resistance because there is no way you can put in 4 contact there. So there are some, so you have to rely on measurements of the superconducting gap and infer information from that. All right. So this is at very small sizes. Then there are effects that come in at a slightly larger size. Now, before I get to that, let me ask if anyone has a question. So it's not just Joydeep and Gorachar. Anyone else who wants to ask something, please go ahead. All right. If not, then the second important part.
Sir, one small question. Sir, I am not in this project, but I am Joydeep. So
It's Devjyoti and Gorachar.
Oh, Devjyoti and Gorachar. I'm sorry.
Yes, sir.
Yeah.
sir, I had a question that here diameter of the particle is important, or how many particles are there, that is important for this nano superconductivity. Because
Yeah, actually, how many particles are there, but how many atoms are there in the particle? But usually that is determined by the size of the particle. Your lattice constant doesn't change so much when you change the particle size. It's the same interatomic forces that are working.
just curious. So using scattering, the particle size are varied. I mean the atomic sizes are fixed, right? So
Yeah. Yeah. So what is the question?
so how these different varying particle sizes are made? Using scattering?
How these are made? So these, there are many ways you can make them. In our experiments, they were made through sputtering. So what you do is that you sputter niobium or lead or whatever you want, and you sputter them within an argon mix, within an argon gas. So depending on the partial pressure of the gas, the nucleation and growth was controlled by that. So therefore, if you had larger, for example, partial pressure of argon, you got smaller particles. If you had lower partial pressure of argon, you had larger particles. Then, of course, you can also control things like substrate temperature, the temperature of the substrate on which you are growing the material. That also will control the size of the particles. So you have, in the growth process, you have various parameters that you can optimize to get different particle size, different average particle size. But this is not the only technique to make it. There are, for example, chemical techniques through which you can make particles. Each of these techniques have some advantage and some disadvantage. There are also techniques which are, for example, more sophisticated techniques. So one of the sophisticated techniques which later was used when scanning tunneling microscopy experiments was done was you go to low temperature on your substrate, which could be anything. I think there it was hexagonal boron nitride. You deposit a thin film of argon. So you are at so low a temperature that argon goes and becomes a solid there. So you have a film of argon. on that thin film of argon, you deposit a small thin film of lead, one monolayer or so. And then in a flash, you evaporate the argon. So you increase the temperature at about 20 Kelvin and the argon evaporates. When the argon evaporates, this monolayer of lead that you have, there the lead atom coalesce and gives you spherical particles. So that was, for example, one of the more sophisticated way to get nice spherical nanoparticles of lead that you could then individually access with a scanning tunneling microscope. So there are various kinds of techniques to do that.
Okay, sir.
All right. So let me then go to the next level. The next level doesn't mean the next topic. The next level means this. This is actually the very small size where you have destroyed superconductivity. But suppose I am at a slightly larger size. So I am at my particle size is such that the Kubo gap is smaller than delta, so superconductivity is not destroyed, but is not very small compared to delta. Now what we will have is large fluctuation effects. So this is one example of fluctuation. Now the problem, so I will be very qualitative here. The reason for that is not that we cannot do it quantitatively, but to do it quantitatively, we need to know Ginzburg-Landau theory. Ginzburg-Landau theory is what I will be starting from next week. We have not yet done Ginzburg-Landau theory, so I will have to necessarily deal with this somewhat in a qualitative fashion at the moment when explaining you. But this is more listing of the topics that you will have to cover and explain in your video. Okay, so in any superconductor, a superconductor, you have all the electrons that goes into a phase coherent state. That's what you have done from the VCS variational wave function. I did the variation and determined U's and V's. You have done the variation with respect to phi in the assignment and shown that all phi k's are the same, which means that all Cooper pairs have the same quantum mechanical phase. Now this is spectacular. This is why a superconductor is a macroscopic manifestation of quantum mechanics, because you have all these electrons here in this large macroscopic body, all of them are phase locked in the same phase. That is what is the basis of Josephson junction, Josephson effect that we will be doing very soon. Again, that will require Ginzburg-Landau theory. Okay, nevertheless, for today, let me just say this. You can describe a superconductor by what is called a wave function like object, which is of this form. Now this is not really a quantum mechanical wave function, but it mimics in many ways the quantum mechanical wave function. So because all these Cooper pairs are in a phase coherent state, all of them have a phase theta, and then there is an amplitude of this wave function. Now, if you take a large superconductor, what happens is that you have this amplitude which is very well defined, and the phase which is also locked to exactly the same value for all the electrons or all the Cooper pairs. However, when you start going to small particles, then you start having a fluctuation of these order parameter. Now, if you are considering one isolated particle like this, then of course the phase, if it fluctuates as a whole over this entire thing, if all the phase of these electrons fluctuate together, I don't care. But now I have to bother about this amplitude fluctuation. Now, what is the main effect of this amplitude fluctuation? The main effect of the amplitude fluctuation, at low temperature you cannot see it. But when you go to Tc, when T goes to Tc, then this amplitude goes towards zero because superconductivity is getting destroyed. So now all that will remain is the root mean square fluctuation in this quantity. So if you want, as you are going towards Tc, this quantity will become large. And in fact, at Tc, this quantity will diverge. So now, what you can show that this fluctuation will be significant at small sizes. Small sizes means how small? Not so small that you have destroyed superconductivity, but then also not so large where you have a very well defined amplitude and a phase. When this fluctuation becomes large, then the most remarkable effect of that is that you start getting fluctuation superconductivity above Tc. And what is the manifestation of that? So above Tc, for T which is greater than but not very much greater than Tc, for a small particle I have this average order parameter that is 0. But still I have this fluctuation which is not 0, and therefore now I will have superconducting effects that will persist. For example, the superconducting gap, instead of closing like this, as you have all derived from BCS theory, you will see that it will start forming this large tail. Now, this effect was also observed some years back. So these things have been predicted long back. But the problem is that there was, first of all, making small particle at nanometer length scale was difficult. And second problem was that measuring was even more difficult. So therefore, there were only very sketchy evidence of such fluctuation effects. And those were, for example, a micron size or slightly smaller than a micron size particle. And those fluctuations there were restricted to, let's say, few millikelvin above Tc. Sometimes even less than 1 millikelvin above Tc. So it was nothing that really convinces you. It is only now with the access of nanotechnology that one can access very small sizes where you can see these fluctuations very clearly. So let me see if I can fish out that paper. I don't have it with me. Yeah, just let me see if I can get that. Yeah. All right, I will share my screen again. Okay, so this is the paper, and you can see, okay, here I can show you a lot more. So these are individual lead nanoparticles that are made in the method that I described. You have this hexagonal boron nitride, which is written as Bn here. Over that, you deposit a thin film of argon. You deposit a monolayer of argon, of lead, and then in a flash, you evaporate the argon. So you get these hemispherical lead nanoparticles. And with a scanning tunneling microscope, you can take the image, and this is how these particles look like. And these are very small sizes ranging from, let's say, less than 5 nanometer to about 30 nanometer or so. All right, so now you can come with a STM tip and measure the superconducting gap of different particles with different sizes, and then you can see again this Anderson criteria. As you go to smaller and smaller sizes, the gap reduces. Here you cannot measure Tc because on this small particle there is no way you can make 4 contacts and measure resistance directly. You have to measure the gap and infer from the gap. And then your gap crashes to 0. So this is where you have the Anderson criteria. The Kubo gap has become larger than the superconducting gap. All right. But as I said, for the fluctuation effect that I want you to cover in this video presentation, I don't need to look at the effect here. I need to look at these samples here, which are small, but not so small as to kill superconductivity. So let us see what happens. If I take a really large size sample, or not very large, let's say 23 nanometer, then the superconducting gap follows BCS, more or less. But when I come to 10 nanometer, look at what happens. It is following BCS, and then it forms a tail, and it does not vanish up to a temperature which is much higher than Tc. This is already more than a Kelvin above Tc. And I think if you, I don't know if there are more data here. So you can see that the smaller you go in particle size, the larger this tail becomes. And this is actually one of the direct proof of this fluctuation effect in superconductors. Okay, so this is what happens when we are at a slightly larger size. Then the next thing that I wanted you to cover is, of course, nanowatts. Okay, Before I go to nanowatts, any question here?
So the prerequisite for the course.
Louder, I couldn't hear. What was the question? Okay, I just cannot hear whoever is talking. Was that Rahul or who
Hello,
was
sir.
that? Yeah.
Huh.
Yes,
So for this, I mean, for the yes. Huh. So for this dependence of this, I mean, delta, I mean, superconductivity gap versus temperature, there is no expression. Just I have to give the, I mean, this argument about, I mean, how why this is fluctuating, why this is not, I mean, meeting, I mean, not follow the proper BCS theory. That's it, right?
Can you see my screen?
Yes, yes, sir.
Do you see the mathematics that is there?
Yes.
Okay. It's your job to read it. Yes, you can calculate it. To what extent you can follow
Okay.
these calculations, it's entirely up to you. Okay.
No. Actually, you just said that we did not do the Green-Landau theory. That's why I just confirmed actually. So okay,
Yes,
then
yes,
I will
yes.
go through this
No,
calculation.
but Ginzburg-Landau theory we have not done. We will be doing it. So that is why you have time till December.
Yes.
Okay. For the video presentation. You start doing, for example, you have to start doing with things that you know, and then things that you don't know, you do it later on. For example, you see that the Kubo gap concept is entirely BCS. So Kubo gap concept does not require any Ginzburg-Landau. The fluctuation effect requires Ginzburg-Landau. So with Ginzburg-Landau, the fluctuation effect, you can do it quite reasonably well. You can also do the fluctuation effect with BCS. That is what is done in this paper. So this paper has two parts. One part was the experimental validation of fluctuation effect. The other was the microscopic treatment of fluctuation, which is done from BCS. Now, the point is the Ginzburg-Landau part, the Ginzburg-Landau approach of dealing with fluctuation is much simpler to do. The disadvantage is that in Ginzburg-Landau you always have some free parameters that you have to get the input and fix from experiments. In BCS, you can try to compute those parameters. So that's the main difference. But on the other hand, the problem with doing the microscopic approach all the time is that the mathematics is enormously more difficult. Okay? So,
Okay, sir.
see, the point is you start reading. Then at some point, when you see that the derivation is just going beyond you, you have to stop there. The point is all of you are entering research. And this is precisely the way you have to approach when you start dealing with a research problem. You cannot start on a research problem by first reading everything in a field. Then you will spend your whole life reading it and you will never end up doing anything. On the other hand, you cannot enter a research problem by not knowing anything of the field and just telling the specific calculation or the specific experiment your supervisor is telling you to do. So you have to find out, you have to strike the right balance between having the broad overview of what you are doing and the mathematical rigor to which you know all the stuff. So this is the purpose of this video project, is to give you a small feel of how to deal with a problem when you are starting on a new field. All right. Okay, so now the third part, which, so whatever I am showing here is whatever is, these are some random things that I thought is sort of essential to cover, but does not mean that these are the only things to cover. As you keep doing literature search, as you keep reading papers, you might get other ideas that you want to incorporate, and of course you are free to do that in your video. The third part is fluctuation effect in nanowire. Now in nanowire, here I would like you to give this search. Give this search on Google, Alexei Bezriadin. This person is a professor in Urbana-Champaign, I think UISC, University of Illinois at Urbana-Champaign. And the cutest experiments that have been done on superconducting nanowires were actually done by Alexei Berziadin originally. So this was done in around, let's say, 2000, between 2000 and 2010 or so. So he had this nice technique where he would produce a small trench like this, and on this trench he would put either a DNA, so a DNA can be like this. So the DNA has no biological implication here, except that it's like a thread, or you can put a carbon nanotube here, and then he would deposit a superconductor by evaporation, so that this superconductor would get deposited on this carbon nanotube or on this DNA. Often that superconductor was molybdenum germanium, and this would become a superconducting nanowire. Now again, the theory of fluctuation in superconducting nanowire dates long back. So in the 60s, 70s and so on. However, experiments on superconducting nanowires started becoming feasible and possible from this 2000 onward, and this was Berziadin was one of the main people who started this game. So what happens in a superconductor? Sorry, in a nanowire. What happens is what we know as phase slips. So what are phase slips? Phase slip is that this is a superconducting nanowire. So it will have again, it will be described by something like this, and this phase theta, which is the quantum mechanical phase of the Cooper pair, is the same for all the electron in this nanowire. However, if the nanowire is thin enough, then what can happen is you can have fluctuation effects where, let's say, a small segment of the size of the coherence length, this becomes normal. Here superconductivity gets suppressed momentarily, and then the phase here and here, they slip. So the phase of this part of the wire with respect to this part of the wire, it slips and undergoes a 2 pi rotation. So when you have this kind of a phase slip, this phase slip is, it produces very tiny very tiny voltage. And of course, this can happen anywhere. So it can happen here, here, here. So it is statistical. It is statistical, and you can calculate at what probability this phase slip will be happening. Typically, the probability of phase slip is this. You need momentarily this region to be excited to the normal state. Now, you know that the difference between the normal state and the superconducting state is given by the condensation energy, half n0 delta square or half mu 0 h square, hc square, whichever you want. So this is the, if you want the condensation energy, and therefore if you have to make a small segment normal, then this will become EC, this is the energy density actually per unit volume, into A, which is the cross section of the nanowire, into this Xi, which is the volume. So therefore, this will be the free energy increase, delta F if you want, required for driving this small segment normal. The probability of that will be minus delta F by kT, and therefore only when this is substantial that you will have any significant phase slip. So that is why you need very narrow wire, so that this delta F becomes comparable to kT. If it is much larger than kT, as normally happens for a thick wire, you will never get this factor would just be too small, and therefore the probability of phase slip would be insignificant. Okay, so phase slip, by the way, is very well described in Tinkham. Again, for the theory of phase slip, you will need to read Ginzburg-Landau theory. I was just trying to find out which chapter, then I will tell you exactly the chapter that you. Yeah. So chapter 8, which says fluctuation effect in classic superconductors, is the chapter that will deal with both phase splits as well as the fluctuation superconductivity that I have told you before. It deals with these two things, and it deals with many other things. So, as I said, if you want to sort of cover more topics than this, feel free. But the essential topic that I want you to cover is these three topics, which are the limiting size of superconductivity, superconducting fluctuations in nanoparticles, and superconducting fluctuations in nanowires. And remember, what you have to cover is not just the derivations that are there in books. You have to also cover experiments. So you need to do some literature search. If you have difficulty in finding materials, don't hesitate to contact me or any of the graders. So all of them are very conversant in these topics, and they will help you with materials. So start reading when you get stuck, either with any concept or whether you get stuck for lack of materials. You read something, you read the theory of something, and you want to know whether what are the counterpart experiments, whether there are experiments at all, or whether it is just a theoretical prediction for which there is no experiment. So all those things, please ask us.
Yes, sir.
All right. So, Surajit, is there anything you want to add, or Sumok?
Think it is okay. So when they will start, they will find the path, and when they will stuck, and then we can help into that picture, sir. I guess
Yeah, yeah.
that
Yes,
is
sir.
the best strategy.
Yes, sir.
That's my point. That you guys have to start it, and then as and when you get stuck, we'll fix these discussions, and we can also use the tutorial time and so on for all these discussions. Okay, so I think today I have finished my time is
One-
up. It's already 7:30. Yeah, Shrujit.
One more just thing that anybody can choose that what sir was talking was the collective pinning. Its look may be little critical from the beginning, but I can assure you it is really a simple stuff. It is, you just read, you will find it. This is the elastic problem actually.
Yeah, actually, the collective pinning. So the problem is that today I have run out of time. I thought I would cover both, but that was possibly unrealistic. So collective pinning, what it entails in the next class, I'll be explaining that. And then from that point onwards, you guys decide. I have no problem if someone does something else, but one has to have a very clear idea. So, for example, Mohavir, you got possibly an idea of part of the vastness of superconducting fluctuation. What you are talking about is superconducting fluctuation in thin bismuth film and so on. That's actually one of our major research topics, though that is one part of the fluctuation effects. So that part of the fluctuation effect, for example, that there are many parts of the fluctuation effect. For example, I have talked about the small particle fluctuation of amplitude of the order parameter. But non-equilibrium fluctuation of the amplitude of the superconducting order parameter is exactly the Higgs mode. So it is, you break the U1 symmetry and then you start getting Goldstone modes and amplitude modes. And this is exactly the analog of the Higgs mode that you have in high energy physics. So that's another part of the fluctuation that one can deal with. So let us right now, for the moment, let's not diversify too much because it will take us possibly beyond the scope of this course. On Friday, let's first discuss collective pinning and vortex lattice melting. And then from that, vortex lattice melting or vortex order disorder transformation. And then from that point onwards, we will see if you still consider that to be too difficult a topic or whether you think that you could sail along.
Okay, sir. So that talk will be on Friday, right?
Yes, that you will have to have it on Friday. Yes.
Okay. Okay.
All right.
Hello.
Sorry, just give me a minute. Hey, Jayati, I'm class teacher. Yeah.
So you suggested also vortex melting can be also studied using fluctuation effects. So I'm not able to relate this thing because we understand Landau-Ginzburg theory and fluctuation there can be encoded in phase and in amplitude of older parameter, but how this thing can also be related to vortex lattice. I mean,
Because melting is a fluctuation effect. When you have a vortex lattice melting,
okay.
what is a vortex lattice? A vortex is actually just a singularity in the phase.
Yeah.
So eventually, when you have a melting of the vortex lattice, it involves the fluctuation of the mainly the phase, not so much of the amplitude there. It involves the fluctuation of the phase that will give you the vortex lattice melting.
Oh, I see.
Okay. So see, the classical fluctuation effect that one talks about in superconductors is what is called as Gaussian fluctuation. And Gaussian fluctuation, there are two theories which are called Ashlamazov-Larkin and Maki-Thomson theory. So this is typically the starting point of fluctuation effects in superconductivity, which gives you, for example, paraconductivity above Tc and so on. If you want to understand why the superconducting transition is not infinitely sharp, but it shows some bit of fluctuation effect above Tc, even in the clean limit. So these are things that you get from Ashlamazov-Larkin and Maki-Thomson theory. So essentially there the Gaussian fluctuation means that below Tc, you have long-lived Cooper pairs. Above Tc, you have still short-lived Cooper pairs. Short-lived Cooper pairs means those Cooper pairs are binding for a finite duration of time and then unbinding. So that is called the Gaussian fluctuation. That Gaussian fluctuation cannot give you a zero resistance state, but it can give you a correction to the resistivity. So you start the resistance, it starts to drop because of the Gaussian fluctuation. So this is the simplest part of the fluctuation theory. Then of course you have to incorporate phase on it. So you have phase fluctuations, and then you apply magnetic field, then you have additional degrees of freedom that you have to consider. The problem in superconductivity so far is that when you deal with fluctuation, dealing with phase and amplitude fluctuation together in a complete theory is something that is not yet possible. So there is no theoretical formalism of that kind. So what one has to do is to take approximate methods and either look at only the fluctuation of the amplitude or the fluctuation of the phase, and then in some ingenious way try to couple between the two. So there is no theory yet which deals faithfully these two on a equal footing.
So do we need to parameterize the vortexes? So like with the coherence length, maybe it will be a good parameter because we are studying the melting of vortices. It means
Yeah.
the
So wait till Friday.
okay,
We'll
okay,
see
okay.
what we are dealing with, and then we can discuss further. All right, about whatever I spoke today, is there any question? If not, we'll end here. Okay? All right, so we'll end here and see you again on Friday. And tomorrow, by the way, there is this, I have shared you the link. There is both a YouTube feed and a Zoom link for this review of the recent discovery of room temperature superconductivity. That's at 4 o'clock. So if you are interested, feel free. I think it will be recorded. So those who cannot make it at 4 o'clock tomorrow, you could possibly look at the look at the recording. But I'm not really sure because I'm not the organizer. I have been requested to give this review. All right. See you on Friday.